Hello and welcome to this video. We are in section 4 of this Pytorch series looking at convolutional neural networks for the first time. As always, all of the code and notebooks for this series are available on my GitHub, link in the description. I am updating this with new sections all the time, and again, open to any recommendations you have for anything you would like me to cover. As I said, we're at section 4, the first Pytorch example, and we're looking at, for the first time, convolutional neural networks. In the previous video, we looked at convolution basics in Pytorch, saw how we could implement a single convolutional layer, how it's pretty much the same as our linear layers in terms of actual implementation, just a different set of parameters. Once we understand the concepts, it's very easy to implement. So as I said, we're now implementing our first convolutional neural network. The only difference really between our MLPs, our multi-layer perceptrons, is that we now introduce some convolutional layers into our network structure. There's a couple of things we're going to go through in this video, as well as our convolutions in our convolutional neural network. So we'll get right into that. So as an example for a convolutional neural network, we're going to be implementing a very old, a very basic CNN. This is based off of LeNet 5. We have an example here for the Wikipedia page. It's LeNet 5 was an old architecture. Was it around LeNet 4 in 1994? So you can see quite old, named after or created by Yann LeCun, who I believe is now a head researcher at Meta or Facebook in their AI division there. So you can have a look at that. But this is based roughly on LeNet 5, the architecture here. Find different sources for the exact architecture, but it's roughly based on that. Okay. So the first thing before we get into the actual CNN that I just want to touch on is that our transforms for our dataset are now becoming a little bit more complicated, not too complicated. We haven't yet got to data augmentation for our datasets, but we're using the transforms for some pre-processing of our data. The main two that we've introduced is resizing and normalizing. So the actual architecture we're using requires a 32 by 32 pixel image. And again, we're using the MNIST dataset. And so we need to upsample. So MNIST is 28 by 28. And we need to, sorry, I'm just going to quickly run this again. So you remember our MNIST dataset of handwritten digits, grayscale 28 by 28 pixels. You can augment the network a little bit, so it doesn't need that, but for our particular permutation of it, we need a 32 by 32. So again, we can just use Pytorch's transforms.compose, and we just need to provide it with a list of transforms. Again, you can have a look at the documentation for the transforms. These transforms include a whole bunch of data augmentation, which we'll look into, as I said, in the future. But for now, we're just looking at some basic pre-processing, mainly normalizing and resizing. So a compose, we just provide a list of transforms, and it will perform these transforms sequentially when we call it. But just as before, we're just going to provide this transform as the transform to Pytorch's MNIST dataset constructor. So resizing will resize the image to 32 by 32, whatever we provide. You can also provide, I think, non-square sizes as well. To tensor, we've already kind of seen. This will just transform the image type. A lot of the time, data sets in that get item function that we saw very briefly, we normally load them as, say, PIL or NumPy arrays. To tensor just converts that to a tensor. One thing to point out, just to note, is that to tensor will also scale, say, our unsigned 8-bit integer pictures. So from 0 to 255, it will rescale them to floats between 0 and 1. So standardize them to be values between 0 and 1, just something to keep in mind. And then our normalization transform. This normalization will basically subtract a mean, divide by the standard deviation to perform our normalization. So as you can see here, the basic operation. And we perform this operation so that our values are mean centered 0 with standard deviation 1. It's a pretty standard practice in a lot of machine learning, not just deep learning neural networks, so that our values are mean centered 0. is something that's nice to have, both positive and negative values. Okay. So this mean here, the first parameter, we provide the mean and standard deviation as a list per channel. We only have one channel for our grayscale MNIST. This mean is just calculated over the dataset for all pixel values. So this is per channel, and standard deviation as well, calculated just for a large batch of images. So again, this will make our pixel values over the entire dataset mean 0, standard deviation 1. So the next point I wanted to touch on is we're now introducing a validation set into our training procedure. So the actual MNIST dataset only has a train and test set. We talked a bit about how we train on our training set, but to validate how good our model is, to validate the performance, we test on a test set. This test set is hidden. It's made up of data, not in our training set. And we use that to validate how good is our actual model. Are we just overfitting on our training set, or is our performance actually good? The additional split we're going to introduce is called the validation split. Technically, we don't want to use our hidden set or a test set during training to validate the performance, because that validation set, you can kind of think of that validation set as what we use to tune the hyperparameters of our model. So our gradient descent through our backpropagation is automatically tuning the parameters of our model, but we are sort of tuning the hyperparameters of the training procedure based on some other validation set. So even though our model isn't training directly on the validation set, we are tuning the performance of our model on the validation set. And it is possible, though maybe rare, that we overfit the tuning to that validation set. And if we didn't have an additional set, a test set, right, even though our introduction, the new split is our validation set, but if we didn't have another split, which is our real test set, that we then test at the end to validate, we may get different results between our validation and our test set. So again, we introduce this validation set that we use to track the real performance of our data model through training. And then once we're finished, we get a test set we use to actually discern how good our model is, not just the model, the actual training procedures, the hyperparameters, the architecture, everything, all right? The training set is what we use to find the parameters. Validation may be what we use to tune the hyperparameters, which you could also do in automated ways. And test set gives us our final sort of score on the actual performance. Okay. So to create that validation split, we're going to do it sort of automatically from the training set. We want to keep our test set whole as a whole test set. But what we're going to do is we're going to take about 10% of our training data and split that into another data set. And for that, we're going to use the Torch utility data.randomSplit. And all we need to do is provide our training data set to that and a list of splits of number of examples. So 90% validation split. This is actually the number of training examples. So 10% of our validation set. So this list just contains the number of examples for training, number of examples for validation. And by defining the generator here with a fixed manual seed. So this is the random number generator. We're creating one with a fixed manual seed, 42. It just means that we can somewhat guarantee that every time we run the code, that split of training and validation data is fixed or kind of fixed. You don't want to rely on this too much. If you want to be more robust or a bit more precise about it, you would create that split, say in a CSV file or some other way to hard code the actual split of each individual data point. Is it in training? Is it in testing? Is it in validation? Using this manual seed as sort of a hack. You don't want to rely on it too much, even though it might 99% of the time be fine. So again, if you want to be precise, make sure you're using a real split, not just fixing a seed or a random number generator, because the results can be a bit stochastic. Okay, so you can see MNIST is 60,000 training, 10,000 test. We're using 6,000 of that training for our validation. So we have a little bit less training data. You don't want to use too much for validation, or else you have less training data. Very simply, again, we're now creating 3 data loaders, but same process as before. We just pass the data sets to the data loader constructor, shuffling true in our batch size, shuffling true for training, think it's true by default, so you might want to set it for false for validation and testing, though it doesn't really matter. We're just setting our batch size to batch size. Okay, let's get on to something a bit more interesting. So here we're creating the architecture for our LeanNet 5 neural network. So the LeanNet 5, which is the sort of architecture we saw up here, consists of 2 convolutional layers and then some linear layers that kind of make up this MLP at the end, which is sort of our decision-making classifier. So we have these feature extractors for our convolutions. There's 2 of them, as I said, and then once we have that features extracted from our input, we have an MLP that will then do the sort of classification. That's the sort of idea. So you can see in this pictorial diagram, we have our input 32 by 32. We perform some convolutions, and that gives us our first hidden layer, which is our output of the activations after the convolutions. You can see we've got 6 channels that are 28 by 28. If we actually look at the architecture, you can see that first convolution layer takes in channels in. As I said, channels, the first parameter is the channels in, which is the number of channels of our input, which will also be the number of channels of kernel. Then we have channels out, which is the number of kernels. Remember, every single conv2D produces one 2D feature map. So that channels out defines the number of kernels, defines the number of 2D feature maps out. Then kernel size 5. So we have a 5 by 5 kernel, and as a result, we'll get 6 channels out, and that 5 by 5 kernel will downsample 32 by 32 to a 28 by 28 size feature map. Again, we have 6 of them, 6 kernels, each producing one of those independently. We have this subsampling step next, and this is just some downsampling methodology. In our implementation, we're using max pooling. So this subsampling, downsampling is just a way to downsample, reduce the spatial dimensions of our feature map. We do this because a lot of our images have a lot of redundant information in them. If you actually look at our MNIST images, for example, right, there's a lot of black background, and the size of the pictures, might be larger than we actually need. So we can downsample and basically throw away some information without worrying too much that we're throwing away any discernible features of the image that we need later on for classification. And we also downsample because it means there's less inputs that we need to perform operations on, less calculations, right? We've downsampled the feature map, which means our convolutions have to stride over less of an input, so it can be faster, more computationally efficient. So it's very common to downsample. We could have used strided convolutions to downsample, but that means that for our relatively small kernel, well, it's not that small, we may not have had much of an overlap, right? So if I was doing a stride above 2 or a larger stride to actually get that downsample, then the overlap might not be great. So if we are striding by 2, then we're not really detecting sort of the intermediate features because, again, our input is very small. So if a particular feature that this kernel was trying to extract was maybe 1 pixel over, but we strided 2, it might not actually detect that. So better to stride with 1 for our actual feature extractor than downsample. But you could stride. Performance for this sort of thing might not be too bad. So we're using max pooling. So just very basically, what is max pooling? Max pooling is a very simple downsampling method. It basically involves having a little sliding window, similar to a convolution, but we're not doing convolution, a little striding window. In our example, we have a max pooling kernel size 2. Default stride from max pooling in Pytorch is equal to the kernel size. So I've defined kernel size 2. Stride will also be 2. And in which case, our max pooling will look pretty much exactly the same as this example here, except they also seem to downsample the channels, but we're not. Their channel order seems to be different. In this example, they've got height, width, channels, whereas in Pytorch, it's channels, height, width. So don't be confused by that. In any case, our max pooling, we slide a little window, in our case, same as this one, 2 by 2, over our input, and we basically just select the maximum value. Maximum value, slide it over. Stride is 2 for us as well. maximum value, down, maximum value, out, maximum value, out. The way this backpropagates through our network is just basically by backpropagating through the maximum value. All the other values get a gradient of 0, essentially. So there's nothing propagating through those. Again, which value is the maximum value of our input? We'd assume would change every time. So, every location eventually over the batch, over the epochs, will actually get gradients, but for any given instance, it might not. It'll get a gradient of 0. The reason why we'd use max pooling or something like this is that, if you remember back to our convolutions, the magnitude out from the convolution tells us how strongly the kernel sort of detected something, how strong was a certain feature in that input. So if a kernel's trying to find edges, that edge detector is going to have a large magnitude on output if it detects an edge, right? So normally we have some activation function, then max pooling. In our case, we're using ReLUs. So ReLUs will zero negative values and just return the positive values. So we're only going to have 0 or positive values. So by max pooling, we're just selecting the largest activation, which will be the sort of strongest activation. Okay. So it's a very simple, very fast, very computationally efficient way to downsample our input. Okay, so let's continue on with the network architecture. We do our subsampling. Note that max pooling happens independently for each feature map. So there's no downsampling across the channels. There are other subsampling methods that might do that, but for the most case, we don't downsample across the channels. We just downsample spatially in the actual feature map. Okay, so then we perform our next convolutional layer. That second convolutional layer is very similar to the first in terms of the actual kernel size, but you can see we're now taking in the 6 channels of the previous layer, and output is 16. So each kernel will be 6 by 5 by 5. Each kernel will combine the features across all of the channels of the previous layer, and we have 16 of those kernels. So each kernel will convolve across each of the channels with a 5 by 5 kernel, and will return 1 feature map. And then, we have 16 of those. So we get a 16 by 10 by 10 from that kernel. We then have another subsampling, which is just max pooling again. Note that we don't need to define multiple max pooling layers because there are no learnable parameters in this layer. It's just a downsampling. It's just a downsampling layer. We can reuse that same layer. So we've got conv ReLU max pool, conv ReLU max pool. So those are our 2 convolutional feature extractor layers. After that, we flatten out our 2D feature map, and then we have 3 fully connected layers, which kind of define our multi-layer perceptron before we get our class activations at the end. So we reshape or change the view. It's just reshaping the output from our last max pooling. So here we've got a 16 by 5 by 5. Note that the input to nn.linear is 16 by 5 by 5 to our first linear layer. So we need to reshape that to be batch size by 16 by 5 by 5. It needs to be 2D for our linear layer. So all we do is just flatten it out, maintaining the batch dimensions. We flatten it out per instance, not flatten it out to a 1D tensor. So it's going to be 2D. We got our output, linear, ReLU, linear, ReLU, linear, and that gets our output. We're going to use the cross entropy loss again, same as the multi-layer perceptron tutorial. So no activation of the output. We don't need to define the softmax. The loss function will include that for us. So hopefully you can see the only difference is that we have this introduction of these 2 convolution layers as well as our subsampling, right? And the idea is that they extract features from an image in an efficient way, right? They can extract these features and their translation invariant. You can detect them anywhere in the image. We subsample to get a smaller representation of our image, and then that goes into our MLP, right? As I said in the previous video, you could hand define a whole bunch of kernels, perform the convolution, get all those feature maps, flatten them out, and then provide that to an MLP, which will actually then do the learning, right? You hand define the kernels, or you could define some learnable kernels and then just incorporate that into your neural network, train the whole thing, get this automated feature extraction, and, theoretically get better features to extract. It'll learn exactly what features it needs to extract to actually perform the classification. Instead of trying to hand define them, trying to work out exactly what your network needs, you just let it work it out for itself. Right? And this is incredibly powerful. It's very, very popular these days for any sort of image, any sort of even video networks. They all use convolutions because they're so useful, they're so efficient, and they work so well. So we'll create an instance of our model. So you can see again, we're printing out the model. As I said previously, this simply prints out the layers that we have in the order in which we define them. This does not define the actual forward pass. Right? So this is not the actual forward pass. If I were to put them in a different order, or if my forward pass was some other order, it would simply just print out the order in which the layers were defined. That doesn't define the forward pass. Just want to make that clear. So we can do a test pass of our image through our model. You can see our batch size was 64, and we correctly get the right shape. So for our cross entropy loss for a single output classification, a single distribution, I should say, 10 classes, we get 10 outputs, which defines our distribution over the classes. We then pass the model parameters and create our optimizer with our learning rate, and we can define our loss function, cross entropy loss. The training and the evaluation functions are exactly the same as before. So really the hard part, or the new part, was just defining this neural network. Once we've done that, we basically sort of abstract away what's actually in our network, and the training and the evaluation and the training loop is exactly the same. So I won't go over that in too much detail because it's exactly the same. Same with our data loader. We iterate over it, just pass the inputs and get the outputs. All we have to worry about is that this network is doing the right thing. We're reshaping correctly and making sure that the output of our network is what the loss function would expect. Okay, we've got our accuracy and loss loggers, and we just run our training loop. Before we do, I just wanted to point out that we have our training loop, and then we have our evaluation on our training and accuracy. You can calculate the training accuracy during the training loop. So you do a forward pass, you calculate the loss, and then you say, well, what's the accuracy of this output? And sort of work out the accuracy of your training set during the training loop. However, that accuracy is not, it's a bit fluid because the model is training while you're testing the training accuracy, or trying to calculate the training accuracy. Well, the training performance is going to improve over the epoch. And so, the accuracy calculated at the start is going to be worse than the accuracy calculated at the end. And so you make an average accuracy over the epoch to get a sort of more precise accuracy. You would then test or evaluate on the training set after an entire training epoch. However, you might not really care about the training accuracy too much. As I said, what really matters in terms of assessing performance is the validation accuracy, which again, we'll calculate after the training epoch. You only need to really care about the training accuracy in that you're sort of comparing it to the validation accuracy to make sure you're not overfitting, right? But once you've sort of made that comparison, you don't really need it in terms of assessing performance. With that, we'll now run the training loop. I'm going to run for 20 epochs. This will take a couple of minutes, and I'll see you when it's done. All right, so we've finished training, and we can have a look at the results. So our training loss has decreased nicely and sort of converged. Again, note, loss is pretty noisy from our mini batch gradient descent. Have a look at our training and validation accuracies. See, we're still going up a bit. We can probably train for a bit longer. See, there's been some slight divergence between the training and validation set, so maybe a tiny bit of overfitting. So let's run our evaluation on our test set. Okay, so there we go. We've got 98.92% accurate. Maybe if we've trained a bit longer, get a higher accuracy. But as I said in the previous MNIST MLP classification video, MNIST is quite easy. I think the highest accuracies these days you can get is 99.5 or 99.8 or something like that. At some point, the images start, or the misclassifications start kind of making sense. You'll get 7s that look very similar to 1s and 1s that look very similar to 7s, such that, even a human would probably misclassify them. So pretty close to perfect accuracy. So let's run some of our test images again through our model and look at our predicted values. So predicted values for these 8 images here, you can see exactly one side with the true values, and visual inspection makes sense. So 7, 2, 1, 0, 4, 1, 4, 9. So looks like it's doing a good job there. So the last thing in this notebook I just wanted to go over was visualizing some of those hidden layers of the classifier. So here I've just got manually done a forward pass with the convolution and then a ReLU, the actual layers of our model. So here is the output for one of the feature maps from the first hidden layer. So this is after the ReLU as well. So you can kind of just change which feature map we're looking at, which 2D feature map we're looking at. And you can try and interpret what sort of features it's trying to extract here. See if we can find an interesting one. So you can see something like this is kind of detecting the edges of our images. See if we can find a different one. That one just seems to be blurring the images, not doing too much. Ooh, so this one looks like it's really getting the edges of our images. More so on the left-hand side here. So this is going from dark to white and not white to dark. So you can see it's always on this left-hand edge because our convolutions, they stride from left to right. So you can see it's finding the edges on this left-hand side, which is going from low values to high values. So obviously this detector is detecting low values to high values, which is pretty cool. Okay, so let's look at values from the next layer. So this is after the max pooling, right? So we've got conv1, ReLU, the max pooling. So we're downsampling, and conv2, ReLU again. So it's a bit harder to interpret these ones because they're quite a bit smaller, but usually you can find something that is at least a bit interpretable. So you can see this one's got some peaks, some of these values. So you can see the tops of these zeros seem to be quite bright. So that's means a larger activation. Ooh. See if we can quickly find something that's a bit more interesting. You can see this one's sort of detecting diagonal lines. Again, remember that these kernels are combining all of those feature maps, all those 6 feature maps of the previous layer. Again, this one looks like it's detecting diagonal lines again. This one looks like it's more detecting some vertical lines. And you can keep doing this, going on and on. Have a look through all of the different ones. This one's more strongly detecting those vertical lines by the looks of it. So you'll see things like this, detecting vertical lines, horizontal lines, diagonal lines, maybe the sort of tops, right, and bottoms of lines, so the points. And all of these features, right, this will get max pooled again and then flattened out. And then those features are what the MLP will use to try and classify. So using this collection of features, spatially oriented, it will then make a decision on what number it is. You can kind of see how that might work. A 1 will have a single diagonal or horizontal line, have a top peak and a bottom peak, right? And if that's there, then the MLP will say, oh, that's a 1, right? And a 0 will have, maybe top horizontal or vertical and two verticals and 2 horizontals, kind of define a 0. A 4's got sort of 1 big horizontal, 1 little one, and 1 vertical. And then the MLP can decide from those features. So hopefully you can see exactly, well, approximately how a network is working without knowing exactly what features it's extracting and exactly what the decision-making process is, but you can sort of intuit how, in a roundabout way, it's actually making its decisions by simply building up these lower level features into higher level features by combining these very simple lines and edges into more complicated features. Okay, so one last thing before I finish this video. I just want to quickly point out this second solution. It's called Solutions with Modules. In this one, all we've done is basically combined our network architecture. If you look in the network script, we've created this class LeNet and we've expanded it a bit more. So we not only have the network defined here, but I've also put in, say, the creation of the data loaders and the optimizer from the parameters. We've also put in the training and the evaluation functions in here as well as our forward pass. This is pretty common to do when you define an architecture or define a model. You also define the training and validation loops such that, maybe you can simply define the model, and that model also comes with its training and its validation functions, so that I can simply define this one class. I set the data set or set the data by passing in our data sets. So I'll create the data loaders with all of the hyperparameters defined in the actual network with our learning rate and our batch size, as well as our loss function. And then when I want to actually train, all I need to do is just call the train model function, which will perform an epoch over training set. And then to evaluate, I just run the evaluation model.evaluate, right? So this is, again, just sort of abstracting away some of the functions so we can focus more on the important parts. And we're going to sort of use this method or structure going forwards because we've seen training loops, we've seen the validation loops and all the other bits and pieces. We're going to focus on particular aspects. And we'll go into more of that in the future, but I just wanted to point out this solution here. All we need to do is import that custom module. So I'll import that custom class from our networks module. Okay, so you can go through this in your own time. Again, that's the only difference. Everything else is pretty much the same. Again, the code is available on my repo, the Pytorch tutorials. And once you've gone through this video, you can start the next section, which is section 5. We're going to go through some more advanced architectures and have a look at what sort of state-of-the-art architectures are and how we can implement those using Pytorch's predefined network architectures. Okay, so I'll see you in that one. Goodbye for now.